been so interesting to hear the varied research that's occurring here, as well as studying chemistry at undergraduate. I actually studied geology at the same time, so hearing the geophysical research today really piqued my interest, and I'm hoping that the talk about my research today kind of offers a synergistic look at carbon capture and storage, and often when talking about carbon capture and storage, utilization of CO2 is often overlooked, and so the reduction of CO2 to useful chemical feedstocks and liquid fuels really offers an opportunity to convert renewable electrical energy into chemical bond energy, and offers an opportunity for storage. But today I'm going to talk about my work on electrocatalysts and bimetallic ones. So this is our technology goal. So CO2 transformation, so capturing CO2 at a concentrated source of CO2, such as industrial emissions. And the reaction itself actually happens in a cell setup that is very analogous to water splitting. So you have electrolyte, and in this case it would be water. And the reaction itself is driven electrically, so ultimately deriving this electricity from renewables, converting the CO2 into chemical feedstocks. This could be carbon monoxide, syngas, methane, and also looking at longer chain hydrocarbons, and these typically represent what we know as fuels, and these are the kind of higher energy dense molecules, and also more valuable products. And so this is where research is really moving towards targeting these higher energy dense fuels. And the stability of chemical fuels offers energy storage opportunities that potentially could be seasonal energy storage, which is really interesting opportunity. But also looking at the transition to decarbonising things that are really difficult. We've spoken today about the difficulties of decarbonising heat, and also vehicles, the difficulties of electrification of vehicles that require high energy dense fuels, and with looking at high energy dense fuels that could just be integrated within the liquid fuel infrastructure that we already have today. But also focusing on the energy requirements for petrochemicals. So chemical feedstocks, mainly fossil fuel derived. I think we overlook the chemical feedstocks and the products that we see day to day that consume that are huge energy consumption. For example, just 26 chemical compounds in Europe generated petrochemically from fossil fuels actually make up 75% of that energy use within the chemical sector itself. And if you look at this as a percentage of the world's total emissions, this is 0.6%. So therefore, this is an avenue for CO2 conversion that we could actually, depending, so this quite small diagram in the right hand corner, depending on the efficiency of the reaction itself, so that's where catalysts come in, the carbon intensity of grid electricity to run these reactions. We could potentially even be looking at negative net emissions of CO2, so sequestering CO2 into the products that surround us and we use day to day. And so this diagram shows the many pathways. I'm just going to get a laser pointer. So this is CO2 molecule, and I've put this diagram up mainly to show the multiple pathways that you can that a CO2 molecule undergoes in terms of so each time, so reduction itself refers to the addition of electrons onto the molecule, and you see a change in the molecule at each stage. There's so many pathways that this can undergo, this reaction can undergo, and hence we can end up with lots of different products. So we have methane, ethylene, ethanol, and hydrogen itself as well. And so this highlights the importance of product selectivity, because as soon as we start getting a mixture of products, then you have to start thinking about the energy requirements of product separation and the costs associated with those. So another important factor for catalysis is the idea that we want to be aiming for singular product selectivity. And so if we look at all these chemical reactions, the top being hydrogen production, which in this case, because we have a source of protons with our water electrolyte, you can generate hydrogen within the potential range that we're running this reaction. But in this case, it's a parasitic reaction. So we aim to suppress the proton concentration to limit the amount of hydrogen produced. And these starred reactions down here are the products that we target here at Newcastle University. So this is ethylene and ethanol. And you can see as we go down this list, we get deeper reduction. So that's more electrons each time, that still are happening stepwise. So if you imagine each step is one electron, when you're getting to things like ethylene, which is a 12 electron reduction, you have so many steps involved in this reaction that kinetically this is a very slow reaction, and that's something else to consider for targeting these higher value chemicals. So here at Newcastle University, this is what our cell setup looks like. We flow CO2 through a chamber, and the catalyst sits exposed to the electrolyte. And here on the right-hand side is a catalyst itself. So it's a thin film copper oxide in this case, that's actually deposited. It can be deposited by paintbrush with a catalyst ink. So in that respect, it can be quite a simple procedure. So if we look at what's actually happening on the catalyst surface, so this is microparticles of copper oxide. We flow CO2 and it diffuses through carbon paper, this diffusion layer. And this reaction is actually happens at a three-phase interface. So our solid phase being the metal particles, the copper oxide, and the reactant of CO2 being gaseous, and the liquid or aqueous phase being the electrolyte, and that's the source of protons. And here the cell design at Newcastle University is specifically set up so that we are targeting higher carbon products. And so by having a diffusion, so the idea that CO2 can flow without having to diffuse through electrolyte, in which unnecessary, unwanted reactions happen between the CO2 and the electrolyte. It flows through the carbon paper itself, and therefore we can actually deliver a higher concentration of CO2 to the surface. We can also have a higher current density, and by using an alkali electrolyte, which you can do when you don't have your CO2 diffusing through the electrolyte, you minimize that proton concentration, which I referred to earlier, is why we get this parasitic production of hydrogen. So our setup here designed for multi-carbon products, and we're aiming for high selectivity of those multi-carbon products such as ethylene. And this is only one, though, of many targets for catalysts and the research that happens for electrochemical reduction of CO2. So in terms of the composition of the catalyst, so back in the 1990s, Horry screened a load of different metals for CO2 reduction, and unfortunately found that hydrocarbon selectivity was only really prevalent with copper catalysts, whereas catalysts such as silver and gold target carbon monoxide. And even with copper catalysts, you're potentially looking at about 30 to 40% selectivity of things like ethylene. So a lot of improvement required in that area. Here at Newcastle University, currently investigating the use of copper, which is advantageous for multi-carbon products, but can we boost the selectivity using gold, which has a high catalytic ability for carbon monoxide production, like I mentioned on the last slide. But carbon monoxide itself is actually an intermediate product for these multi-carbon products. And so if we can increase the prevalence of carbon monoxide on the surface of copper through like a spillover mechanism we're imagining from the gold itself, potentially copper could have a lower over potential at which it can produce multi-carbon products. So that's our thinking and behind our approach. So currently, the synthesis of copper oxide has occurred in a microparticle form, producing catalyst ink, doctor blading this onto carbon paper, and then after having this layer of copper oxide, actually electrodepositing gold onto the surface. And so this happens in a setup. This is the first iteration of this, just a proof of concept. But yeah, running a reducing current through the copper oxide GDE and being able to deposit gold onto that surface. And yeah, so this is a cyclic voltammogram, and this peak here at 0.1 volts was the appearance of the gold once it had been deposited. And we were aiming to deposit 1 weight% of gold onto the gas diffusion electrode. Another technique that we've been using is the photodeposition of gold onto copper oxide, and just looking and studying whether we can get different morphologies. And yeah, so this is where we're at the moment. We have a cell set up that favours multi-carbon products, but still looking at our deposition techniques, aiming to use both the electrodeposited and photodeposited gold copper oxide samples, and critically calibrating our gas chromatograph to enable us to quantify those hydrocarbon products and be able to calculate our selectivities. With many thanks to my supervisors, Eileen New at Loughborough University, Elizabeth Gibson at Newcastle University, and the postdocs that have supported this research as well. Yeah, thank you very much. I'm happy to answer any questions.
Thank you very much, Ella. That was really interesting. It's amazing what you see sometimes. I'll just open the floor for any questions. I only really have a comment, which is there a way that we could use this to sort of double our hydrogen capacity? If you know what I mean. If you're producing blue hydrogen, could you sort of whack it around again, take the CO2, create some more methane, and then try and produce hydrogen from that again? Is that something that you reckon is possible, or is that just like Star Wars?
Yeah, well, I suppose I was criticizing the production of hydrogen as part of this reaction setup, but in terms of the research of other groups, they've been looking at producing controlled mixtures of carbon monoxide and hydrogen, and this is syngas that you can then use for synthetic processes of useful chemical feedstocks. So there's so much tunability within kind of product selectivity, but in terms of the research here, we're aiming to kind of look at moving away from hydrogen production, because it doesn't happen very energy efficiently in this setup here. Yeah.
So I don't. And any other questions from the chat? No. Is this scalable industrially? Like how scalable is it? Could you tag it onto the side of a power station, or is that just too large? Would you require too large an area, too much water, too much catalyst?
Yeah, I think that's really interesting. The opportunity to, I suppose, delocalize this electrosynthetic process and put it on site with a point source of carbon dioxide, which would mean that you wouldn't have to transport your carbon dioxide around and base it there. I suppose another thing to mention about using source of CO2 from an industrial process is that you might have other contaminants within the CO2, such as NOx, which could poison your catalyst. So another research area is looking at unpure CO2 feed for this reaction specifically, but based upon kind of electrolyzer technology that exists for water splitting, it definitely, if we mimicked the technology scale up there, it would definitely be possible. Yeah.